Unmute the video and we can start the live. We are in live, Pratik.
Okay, is my video visible? So I've turned the video on. Yeah, I've turned my video on. Is it not visible? Okay. Is
It is visible. Yeah, it's visible.
okay. There's just one student currently, Govindam Priya. Are you here?
Yes, I'm there.
Okay, hello. Yeah, so you can start asking any questions that you have till now. Okay. Whatever questions you have till now. Well, but are we on we are on week 6, I think. So do you have any doubts or any question that you want to ask?
Like so far, I've went through only 2-3 weeks of course,
Mhm.
which included that SVD, ECA.
Okay.
Like latest, I'm not aware of that.
Okay. So from what you've gone through is how are you finding the courses, everything clear, able to understand everything?
Like it's a bit difficult. Like I've seen the video lectures.
Mhm.
Though those video lectures are fine, but I face little difficulty in understanding.
Okay.
Basically, I'm from a mathematics background.
Okay.
Like I'm good at mathematics, like matrices, calculus. I'm good with those things.
Mhm.
But when it comes to applying these mathematical techniques in programming, I'm not able to follow these things. So what I did, I just went through few examples that was very brief, like it was not very depth.
Mhm.
Like for example, eigenvalues and eigenvectors, I went through those things. I've solved some questions on that mathematically.
Mhm.
Programmatically it was very easy.
Okay.
So when it comes to SVD, that is singular value decomposition, basically these things are like it's very difficult to understand and it's very difficult to implement too.
Okay, I understand, especially for someone who's not who doesn't have a lot of programming background, it can be difficult. But that is the thing about application of all these, that if your mathematical background is strong in this, you don't have to limit yourself to a specific language. If you're more comfortable with, say, like MATLAB or R or any other language or C, whatever language it may be, if you know how to apply what the mathematical theory of a certain concept is, then it there is a what do you call that? There is a slight adjustment period in the beginning, but you'll soon find that once you realize how these mathematical concepts translate to programming, say in the case of Python, once you figure out how the basic syntax of NumPy works, or how the basic syntax of MATLAB works. So that takes a little bit of time, but after that, you'll find that it's actually it'll be very easy for you, especially for you because you already have a mathematical background. So you just have to do the job of translating it into code. So it will take a little bit of adjustment time, but I'd suggest you just practice more and more with simple stuff. Say how to basic stuff, very basic stuff of linear algebra, how to multiply two matrices, uh, how to do that in code, how to transpose a matrix, how to calculate the inverse of a matrix, like these basic operations. Once you get the hang of these operations, then all you need to do is just combine these operations together to perform, say, SVD or whatever else it may be. And in many cases, you don't even have to. Like SVD, NumPy has an extensive library of linear algebra functions that you can just pick and use. You don't have to implement them from scratch.
Like I've seen a few examples on that. In this case, those are very simple functions in Python. That I felt it very nice when I saw all those simple functions doing a lot of things there. But I'll be getting familiar with this language. And coming to my assignments, I'm not able to get even half of that. I'm like very afraid. Will I get even through with this assignments or not, and what? What about that? As so far, I've given four assignments. I didn't even scored 50, like 60% above. All the things are very like it's very down to 50%. Like, will this affect like what all to do to improve in the other assignments?
I mean, what I can suggest is that you just make sure that you're following every concept in the lecture, because that is what most of the assignment will be based on. Now, because it is an assignment and because you get a week to solve it, some of the questions might be out of syllabus. Some of the questions might not be directly covered in the lecture, but most of them are. Most of the questions would be covered as it is in the assignment. Just the values would be changed or just the concept would be mentioned. Just take your time on every question, because you have a week to solve. Like what are the 15 questions in a week, so 2 or 3 a day. If you do it, you'll be able to finish the assignment on time. So don't feel the need to rush. Just take your time, think about the answer, why you think it's correct, and more importantly, when you mark an answer, just think about why it cannot be incorrect. So if you try to find a reason that your solution may be incorrect and you are unable to do that, then you can be confident that your answer is correct. Or for some questions that are not theoretical, what you can do is that you can perform many checks. Say, if you have decomposed a matrix into its constituent matrix, you can see if you reconstruct the matrix from the components, is it close to the original matrix? If it is, then your solution would be correct. But if it's an entirely different matrix, then you would know that your answer is incorrect, and then you try again. So just things like that you can do to, do an assignment properly. But don't let that dishearten you, because this would be, the assignments would be relatively difficult when it comes to the exam or when it comes to any live quiz or something, because for an assignment you get a week, but for an exam you will get 3 hours. So that's why there would be, I don't think that the exams or whatever it is would be as difficult as the assignments. So that's usually not the case.
How will be the exam pattern, and when can we have time? Like we are having very short time to prepare for the exam. So what all the techniques would you like to suggest to prepare for this exam?
Just make sure that you are covering the lectures. I'm not sure, really sure about the pattern right now. Maybe of the questions we would still working on. It would have MCQs and it maybe have some short or long theoretical answers. Most of it would be MCQs, but nonetheless, what I would suggest is that go through the lectures and like make notes of the lectures, make notes of the important points as you go. So when it's time to prepare for the exam, you don't have to go through all the lectures. And you can just go through those notes over and over again and get prepared. Just have an idea about what concepts are covered. So the lectures will be important for the exam. So make sure to cover them thoroughly.
Thank you so much.
No problem. Yeah, I guess nobody else is joining.
I think only 4 participants are there in the room.
Yes. So excluding you, there's 2 PS, me and Siraj, and 1 admin from NPTEL. Okay. I guess we can. I'll just wait for 5 more minutes and then we can end the stream.
Like, I have one more question.
Sure,
Like,
please ask.
like these all are techniques to decompose the large matrices into small matrices, right?
Yes,
So
yes.
in real life, how we gonna use all these things? Like, really, industries use all these things in their activities? Like one real life example to make my understanding more better.
Okay, so when it comes to industry, what we're usually dealing with is a very large scale problem. So your dimensions would be extremely large. Even if you decompose in most of the cases, and right now there are better ways to do it. So the reason we started the course starts with PC and SVD is because those are some of the fundamental techniques that were used in the industry to say for facial recognition or many other things, or just basic storage. So those were techniques that were used in the industry. But now, if you look at the current state of the art, we have moved beyond that. So we have moved into the area of machine learning and optimization, say neural networks, the things that we cover further down the lectures. So that's the reason why it's so one of the reasons why we still teach that decomposition of matrices and all that stuff is because it is important to scale up what you know about the techniques that we currently use. So without having the context of why we use the techniques that we do currently, it's difficult to truly understand the technical details of it. For example, the reason we use machine learning is because when you have a function that is not convex, so for that function, it's not easy to find a global minimum. So if you have a convex function, it's extremely easy. It's very straightforward to find the global minima of a convex function. But that's not so simple when it comes to a non-convex function. So in that case, we approximate the global minima. So, and in real world, we rarely encounter a convex function in the field. So it's very rare that you will have a data set that would be easily mapped by a convex function. So that's why as we start to get more data, we have started moving towards approximation techniques like machine learning, neural networks, and back propagation to approximate these minimas of loss function instead of having, the techniques that we initially teach in this course. Does that make sense? Are you there?
Yes, yes, I'm there.
Okay, so does that make a little sense?
Yes. Like, if these things are so difficult, like it's very large, the data sets,
Mhm.
the parameters they use in this and the techniques they use, if this is so difficult, how people are managing like billions of parameters, how the development is taking place? And
Yes, okay. So that's an interesting point in history because neural networks aren't really anything new. So neural networks, the current state of the art that we use, have been theoretical, a mathematical concept since the 1960s. But we had two problems because of which we couldn't use them for a long time. So we started using neural networks in early 2000s, mid 2010s. That's when it really took off. So the reason behind that were twofold. First, that we didn't have enough hardware. We didn't have enough powerful hardware. Like if you see right now, a regular laptop has a GPU that would be equivalent to a supercomputer in like early 2000s. So the hardware has gotten very powerful. That has enabled us to perform these many computations, many different, very large scale computations. And second is because we now have access to a lot more data, so we can approximate our solutions more easily. Now, when it comes to hardware, that plays a role because essentially what neural networks are is just matrix multiplication. That's fundamentally, not really, I'm simplifying it a lot, but training a neural network is essentially performing a lot of matrix multiplications. And GPUs are quite efficient at that. So we have very efficient algorithms that we can parallelize, and GPUs are very efficient at performing those. So that is why we're able to take such a large number of parameters and train them.
it's all about hardware.
Yes, mostly hardware and data. Now, at this point, we have access to a large amount of data. So yeah, currently we can say that the limiting factor, bottleneck, is the hardware. Yeah. I guess I don't think anybody else is joining.
Sir, am I audible?
Yeah, hi Tanuj.
Hi, sir. Sir, I have some doubts. Pretty like we use gradient descent, and
Yes.
we have to calculate derivatives.
Yes.
So, what we will do in case if the objective function is not differentiable?
Okay. Right. So there is a concept called sub-differential. Do you know what sub-differential is?
No, sir. I have heard this first time.
Okay, so sub-differential is, say you have a continuous function that is differentiable everywhere, right? And now think of say non-differentiable function. There is an activation function called ReLU.
Okay.
So what that does is that up to a certain point, it has a constant value. Say up to 0, it has a constant value of 0. And after 0, say for the positive numbers, it has a linear value.
Okay.
Right. So it is an angular function. For negative numbers, it has the value 0. And for positive values, it has linear, it gives a linear output. Now, this function is clearly not differentiable. It's at least not differentiable at 0 because you have a coordinate point there. But what you can do is that you can take subdifferential of the positive side and the negative side. Take subdifferential of the parts where it is differentiable, and then calculate those.
Okay.
Yes, so that is one way of doing it.
Okay, and I think apart from this also there might be other algorithms to optimize.
Yes, what we do is that if our function is not differentiable, what our first step to optimize that function is to approximate it by a differentiable function. So we have a lot of different methods to approximate a function in higher degree. So you in first degree, second degree, or third degree, whichever fits your whichever function fits your requirements best. So we try to make it easy, so just like in linear programming, or just like in convex optimization. If you have a linear program, many times what we do to solve it is we convert it into integer programs, or we convert an integer linear program to an MIP, or a simple continuously linear program, based on what we want our solution to be, based on how much error we can afford in our problem. So it's the same case here. If you have a non-differentiable function, you try to approximate it by a differentiable function and then take on there, go from there.
And sir, in case of gradient descent, the idea is if we move in the direction of negative slope, so we will get the maximum decrease in the value of objective function.
Yes.
So we can say like this: if we move in positive direction of the slope, we will get the maximum increase in the value of objective function.
Yes. I guess, yeah, that would make sense. Yes.
This is correct.
I would need to check this. I haven't really thought about this. I think it should be correct.
Okay. And so regarding weights, if we change the initial weights, so the solution which the local optima which we will get through gradient descent, it might be different.
Yes.
So is there any way we can decide on the weights, like which would be the best combination or a better combination of weights?
Yes. Okay. So there is no, what do you say, an analytical way to decide what the weight should be. Like there's no exact way, but there are many heuristics that you can use. Most of them are, depend on the activation function that you've chosen. Say, one of the ways is just the basic way is just have all zeros in the weights. Another is just have a random, like totally random selection of weights. That is one way, but these are very basic ways. So then we start getting into some specialized way. Say, for example, if you have I just have one method that is coming to my mind. So if you have a tan H activation function, for that, what we use, we often use a method called Xavier's method. What that is that if you have n number of samples, you initialize your weights by sampling from a uniform distribution that goes from -1 upon square root of n to 1 upon square root of n. So you define a uniform distribution from -1 by square root of n to 1 upon square root of n, and then uniformly sample your weights from that distribution. So that's a Xavier method, and it works best for tanh function. Like similarly, there are other methods that work well for, say, ReLU function or sigmoid function. So these are some heuristics that you can follow. You can look them up. You can research them when you're implementing a model, and you can find many such heuristics.
Okay. And sir, is it guaranteed that this gradient descent, it will always give us some local optima? Guaranteed?
Well, let me just think about it, whether we can have a theoretical guarantee. I mean, I guess you can give a theoretical guarantee of convergence using gradient descent or different variant of gradient descent. Yeah, you can probably give a theoretical guarantee of convergence at some local minimum.
Okay. And sir, I have posted one question in that Google form also regarding that neural network. How to write objective function.
Okay, yeah. Okay, so S, I think I did that. Just let me check. I don't know what S and H mean.
By S means I meant training sets. How many training sets are there?
Okay, cool. Okay, so what it would depend if you have, say, H. Let me just share my screen. This. Is this screen visible?
Yes, sir, it's visible.
Okay. So if you have, say, number of samples equals S, number of output neurons is H, right? So, so if the number of output neurons is H, your output is an H cross 1 vector.
Yes, sir.
Right? So, what do we, so first question that you should say is, what do we have available? We have a data set of X, Y. So where X is a vector, say empty vector, sorry, and Y is H dimensional vector. Now, this is the information that you have. And now to get the objective function, I'm just giving a basic, say, MSE error, minimum square error. What you have to, what you generate basically from your neural network is prediction. Prediction Y. So okay, so this is the prediction that you generate. Now, what your goal is in the objective function is to minimize the error between y, let's say y, and it's this I. For the ith sample, yi hat is your prediction. What the objective is to minimize the difference between yi and hat yi. Okay, so let's say that is y I minus y and y I, and just let's just square this. Now this is for one sample.
Yes, sir.
So if you have S samples, you take the sum over S and then you divide it by yes. So this is your mean square error. Take the difference, you take the mean of the difference and square it.
Okay.
So this is one objective function.
Hmm.
So similarly, there are many other many other objective functions. So this is MAC is used in the case of regression. Say if you have classification, there is a cross entropy loss. Cross entropy loss is something like again sum. You take a sum, and it's something like y into say log of y into log of y hat plus 1 minus y into log of 1 minus hat y, something like that. So this is another type of, so this is a different type of cost function. So in a similar way, the same thing happens, is that y hat is your m cross 1 vector, h cross 1 vector, your y was your target, that was also an h cross 1. So in this case, y has to be, if number of output neurons is h, that can only be the case if your y is of the same dimension, because that's what you want to compare against.
And sir, in this equation, this yi minus y hat square, this equation,
Yes.
this yi or y hat, it will be a matrix of h cross 1.
It will be vectors. I mean, see, if you take say a regression problem, this would be y hat and yi would be a real number. Say in here for binary cross entropy loss, it may be something else. So it depends entirely upon what you're trying to minimize and what the specific objective of the function of your neural network is. So having that information, yes.
Sir, this equation is correct in case in that outer layer there is only one neuron.
Yes.
But if I have more than one neuron, so how I will change this equation? Either I have to.
Yes. So what we have is one other thing. Say when you perform some the neural network, say when you have a digit classification, let's take that example. You have a neural network that classifies digits, handwritten digits. So what you have to do is that in an input, you get a handwritten image of a letter, and you have to find out which letter it is. So that is a classification problem. That's a multi-class classification problem. And that your output would be a vector of 10 neurons, right?
Mm.
And what our goal is to find the neuron that has the highest value. I'm just giving one example of where a multiple vector is given. So that is yes. So in that case, what we do is that we select a neuron that has the highest value, but that is more often not an optimum way to do things. So what we instead do is that we create another cost function called a softmax function. Softmax function is basically a sum of probabilities in the denominator and the probability of every neuron in the numerator. So the entire sum is equal to 1. You basically normalize everything. So that's one way that you use, you create another cost function in a way where you have multiple neurons in output. So again, this would, again, if you have a vector output, if you have H number of, what I'm trying to say basically is that if you have, say, H number of neurons in the output, that does not really confine you to one type of cost function. What really matters is what kind of problem you're solving. So the objective function would change accordingly. So there's no one single objective function that you use with every problem or every regression problem even. So based on your problem, you choose a cost function that fits your need.
Okay, sir.
Yes.
Sir,
Yeah.
recently, like I was working on something like this, like a function takes an output, like input will be a text thing, like let's take paragraph. What this function does is it takes this text and it gives the answers for the questions that we ask.
Okay.
Like so the input will be the passage and the questions.
Yes.
Like output will be a text again, it will give out answers. The given paragraph.
Yes.
So we like I've got the answers, like when the paragraph is not very lengthy, when the paragraph is very short and the questions are straight, it's giving good answers. Like when the paragraph is very big and the questions are very short, it is giving good answers. If the paragraph is like medium and we are putting in 2-3 questions at a time in the same question, like it's not able to give good answers that we expect, that I was expecting. So what are the things I have to do to make the, like to get the output as I wish, like how accuracy indirectly?
So there's no one single answer to this problem. Okay, Tanuja, I think I remembered the answer to your question. I don't think we currently still have a theoretical guarantee of backpropagation converging. So I think that's still, I just remembered that is still an open problem. We don't have a theoretical guarantee that backpropagation converges. We just practically realize that it does. So that's still an open problem actually.
Gradient descent.
Yes.
Okay, sir.
Okay. Anyway, so back to the original question. There is no one way to figure out what's wrong with your model. So what's usually the best way to do it is to try to narrow down what specifically is causing the problem. So because right now, if you don't know exactly what's causing the problem, it can be any number of things. It can be that you haven't trained your model enough. It can be that you have trained it on, say, biased data that is biased towards shorter paragraphs or doesn't have enough long paragraphs. Or it can be that you're choosing the wrong cost function. It can be that you're choosing the wrong architecture. It can be that you haven't that your parameters aren't tuned properly. So it can be a very large number of things. So the best way to figure out what's causing the problem is to isolate certain variables. By isolating, I mean, say for hyperparameter tuning, you take the same data, same architecture, and try different hyperparameters, different combination of hyperparameters. That's basically called hyperparameter tuning, or grid search. You can look up what grid search is. So that's one way to narrow down if hyperparameter tuning increases your performance. The second way is, say you narrow down, you isolate the cost function. You check out other research that works, that has done similar work to what you have done. Their code and architecture would probably be available online officially. And you would be able to see what kind of loss functions have they used. And if you see 2-3 papers that have used the same type of loss function, and your loss function is something different, then you know, okay, this probably is not the right way. And similarly, you try to isolate the variables that can go wrong, because there is a lot of them. So just focus on one thing at a time to see what improves your performance to a degree that is acceptable to you. Because we have 5 more minutes.
Sir, in one of the slides in which sir was explaining about local minima, so mathematically he has defined like norm of x minus x star has to be less than or greater than epsilon, something like that.
Yes. Yes.
So I just want to confirm this mathematical equation, is it this is valid only for unconstrained optimization?
I mean, no, not really. That is what was given, I guess, was the basic definition of a local minima. What local minima is that that point that you're saying is a minimum, is the minimum in its immediate neighborhood. It might not be minimum everywhere else, but if you draw a circle, a sphere within a certain distance, it would be minimum in that case. That boundary may be however big, but through the definition of that, it should be greater than or less than some norm. Through that, greater than less than epsilon. Through that, what we are trying to demonstrate is that that point is basically minimum, has the minimum value in its immediate neighborhood.
Okay, but it might happen that let's say we have different directions in neighborhood. I can move in any direction, and
Yes.
if we are taking constraint programming, so we cannot move in some direction. So that definition won't be valid, because through that norm we are creating like a ball.
Yes, but you can always change your epsilon to have any number, any small number of like a very small size, because epsilon that you take, the radius of that ball that you take, that is infinitesimal. You can increase or decrease it however much you want. So there will always be a possible ball that you can create.
Okay, so that equation is both for unconstrained as well as constrained programming.
Yes.
Okay, sir. And one more doubt I have, sir. Let's say I have one objective function, unconstrained, and I want to know its local minima. So what I will do is I will take its derivative, find the variables where that derivative is 0, then check for second order sufficient condition.
Yes.
If the Hessian is positive definite, so the point will be local minima.
Yes.
So like this I can find. So if like this procedure I can find a local minima, then what is the need of gradient descent?
Yes, because it's not always possible to calculate the Hessian. And even then, you might not always, if you're not able to find, if you're not able to find a Hessian, that still doesn't mean that there's no minima. You can still find a minima, you're just not able to use this method. Or this method works best in case of convex problems or a convex function. But when you go into non-convex functions, these criterias don't really always give you the correct answer. He'll say there may be some cases where you're not able to find a Hessian. Not that it's not positive semi-definite, but you're not able to find a Hessian. But there will be a minima in that case as well. There could be a minima in that case. So that's basically the reason, because like I said a while ago, the reason behind we using gradient descent and other approximation methods is that most of the time in reality, we don't have access to functions in real world that exhibit proper behavior, like convex behavior or something that have a proper defined global minima. We don't have that. So when you go into non-convex problems, these conditions might not always be satisfied. And so the best you can do is that approximate a minimum. And that's what we use gradient descent for, because that's much easier than trying to calculate the Hessian of a million cross million matrix.
Okay, sir.
One last question
And so
from
this we
Yeah, yeah, just go ahead.
uh, like have you heard about this GPT-4?
Yes.
Like, can you give me some skeleton up behind it? Like, what all they use, what all they do inside?
I haven't done much. I don't really know much about NLP, natural language programming. So I don't think I'd be able to best explain it. But these kinds of models are called, they're called large language models. They are based on a structure, they're based on an architecture of models called transformer models. So transformer models were designed first, they were invented by Google. So that's the architecture that GPT is based on. The T in GPT is for transformer. So that's the kind of architecture they use. But other than that, I don't really have much knowledge about natural language.
No, that's okay. That's fine.
I think Tanuj, you had one question. Was it you or-
no, sir. I was just confirming that regarding solutions of assignment 4.
Mhm.
So when
Oh,
we can
that
get
still hasn't been updated.
no, sir.
Okay. I'll look into that.
And the notes which you have shared. So
Mhm.
first of all, we are really thankful. And another thing is in that week 6, linear regression and this was not there.
Okay.
And
Okay.
linear regression, and just after that, another topic sir has taken. I'm not able to recall that topic.
For week 6.
Yes, sir.
Okay. Okay, I'll check that as well.
So these two things.
Okay, sure. No problem. Okay,
So, I need notes for this, like a proper notes. If you have,
did you see the did you see the message of the discussion group? I think we have shared the PDF slides there. We have shared a Google Drive link to the slides there.
I didn't attended that session, I think.
No, it's on the discussion, this sort of discussion forum. And it's a discussion forum. If you've registered with the course, that you should have access to a discussion forum. It has, in that I've posted a link to Google Drive. That has all the lectures and basically the lecture slides.
Okay, I'll try to look into that.
Okay.
Thank you so much.
Okay, no problem. Okay, thanks everyone.
Thank you, sir.
Thank you.